those people can represent a very serious challenge to operating a mine or a quarry operation in ever increasing areas of the world. Go ahead, Andrew. I have 3 slides here just as an kind of an explanation of how this has gone. There'll be 3 mining operations that you'll see here, actually 4, and you can see the development around it. But the important thing to remember is when these places were developed, there was nothing around them. And I often spend time in mining operations that don't have neighbors or anybody nearby, and they kind of, their opinion is, well, Stuart, that's fine, maybe where you live, but I don't have to deal with it. You have no assurances what's going to happen anywhere nowadays around a mining operation. And therefore, over the course of time, you really can't predict what the circumstances are going to be. And if you're not prepared for that, it can have long-term complications. Andrew, just run through the next 2, a couple seconds each. Here's an example of 2 quarries literally right next to each other in a downtown city, a river going in between. And one of my favorite examples of people moving in close to quarries is on the next slide. This is on the west coast of the United States near Portland, Oregon. And you can see the houses. This is a helicopter view of the mining pit. And the house I have an arrow. Can you hear me now?
Yes.
Yes, sir.
Sorry, that was my internet dropped off. So, but anyway, thank you, Andrew. You see the value of that house sitting there, and it is 53 feet, so less than 20 meters from the swimming pool in the backyard to the high wall, and you're looking at a value of close to $2 million US. So, needless to say, people spending that kind of money on real estate are not very tolerant for what's going on, and usually the first questions they ask is, when are you shutting that place down? So it puts a lot of pressure on mining operations to do things right and do everything they can to minimize that community footprint. Go ahead, Andrew. So when we look at improved blasting designs, we look at several things. We have increases in electronic initiation systems that have brought a whole new world to us. And that has allowed us to do some new things with vibration. As far as active vibration cancellation, we can do more real-time analysis and look at using alternatives for blasting. We must say, though, that a lot of times things that we try to do to make improvements can be are severely hampered by either people's pre-existing beliefs in what works, or by regulations that don't allow us to use the latest technology. So it's important not only to understand how it works, but be able to relay that message to people if you need to get the point across that there is a different way, a better way to do things, and how we can improve on what we're doing. Okay. Okay, so let's start talking about fundamentals for vibration control. And Bill touched on this last week, and again, I think it's worth going back over. When we detonate a blast, I mean, we're given a given amount of energy, and we're really going to do 4 things with that. We're going to break rock, we're going to move rock, and whatever doesn't go into that is going to make noise and shake the ground. There's nothing else to be done. Energy can't be conserved; it has to be used, and it's going to go into one or more of those 4 methods. So you can really make a talk on vibration control really, really simple. I can make this easy for you guys. The best form of vibration control, it's a good blast design. And you have all the latest technology, vibration software for vibration control. If you don't have a good blast design, it doesn't matter. It can't fix things for you. The first thing you have to do is have a good sound blast design and have effective implementation of that in the field. When you're doing that and you're convinced that you've got those metrics put in place, then you can look at additional technology to fine tune for your vibration control. Until that's in place, you're not going to get where you want to be. Andrew? I just want to spend a few minutes. We touched on the 8 millisecond definition last week, and just a little bit more detail on that because it kind of plays into everything we'll talk about here. This is the data from the original study back in the 1960s that led to the 8 millisecond delay criteria or definition. And you can see it's for 3, 7, and 15 hole shots. They were shot with 4 different sequences instantaneously with 9 millisecond, 17 millisecond, and 34 millisecond delays. And when you look at the results, there's no real consensus whether a fast or a longer delay gives the lowest vibration. The only thing it tells you is using a delay is going to give you some form of vibration control versus shooting instantaneously. But that's really all that we get out of that, and there's no magic that comes from using a specific delay. Next slide. And if we get into that and really look at what went on in that research and what was available back in that time period, they basically used the technology that was available in commercial mining. And at that time, 9 and 17 millisecond delay detonators were very common and available, and that's what they used in those studies. At the time, they were electric, not electronic, but electric detonators. Were listed with a plus or minus 1 millisecond accuracy. So the writers of those papers said, well, then if we have plus or minus and we use 9 milliseconds as our shortest delay, then probably 8 milliseconds was the minimum delay that we used in these studies. And really, their report came out and said, if you use delays, it's a means of reducing vibration. And through that came the 8 millisecond criteria that we have. And if 25 millisecond detonators were available and they used them back then, we'd probably be sitting here talking about the 24 millisecond criteria. There's nothing magic about that 8 milliseconds. And as we found since the introduction of vibration modeling, it really doesn't serve very much of a purpose anymore. But we have it. It is used as a definition for charge weight per delay, which leads us to the next slide, which hopefully we're all semi-familiar with, is our definition of scale distance. It's a function of the distance between the shot and our given structure, and then using a scale root of pounds. And obviously there's a similar formula for using it with metric. Sorry, I don't have metric in here, guys. And that's really where our definition of scale distance has come from. Andrew? But when we really look at the data from that study, and this is really important, this is the data that was used for some of those early studies in the 1960s and early 70s for vibration. And here's a plot of scale distance on the x-axis, you can see on the bottom there. And then we also have particle velocity. And again, I'm sorry, everything's in imperial here on the y-axis. But you notice the scatter that we have throughout the plot here of data. And just as an example, I put a line on a scale distance of 20 and then looked at where the data intercepts were. And excuse me, this is really for a scale distance of 18. But along that line, a scale distance of 18, there was shots recorded with a scale distance of 18 that had a peak particle velocity of 0.14 inches per second, and then other ones as high as 2.9 inches per second. So basing vibration prediction or vibration control in your shot design based on scale distance, it's better than nothing, but it really doesn't get us where we need to be to have any confidence in our results. Andrew? So that's led us to use things kind of on the passive side for vibration control when we need to reduce things. We've reduced charge weights per hole. We've used decking, reduced shot size, smaller hole diameters. Been there, done all that. Does it work? Yes, to a certain extent, but it all comes with a cost, whether it's in longer time more labor, more drilling costs, more product costs. Usually, it's a hard balance to achieve. Andrew? So what we have nowadays that we can use, especially with electronic detonators, is active vibration control. It's the concept of linear superpositioning that we've used, and we're going to demonstrate that. Um, the use of electronic initiators has greatly enhanced the efficiency of this technique. And when you marry that with some of the new concepts in software design that Andrew's going to show you in a few minutes, it's really exciting where we are and what we're able to do to get on the front end and get control of vibration. Again, um, a lot of my experience is with off-site vibration, but I have certainly have done my share of near field, and the rules of and laws of physics are the same near field as far field. So the same theories and technology works in both places. Andrew? So we want to begin with seismic wave interaction because this is where it all starts with. And hopefully this is review for everybody, but just to make sure we all understand, when we talk about seismic waves or vibration waves, we're really talking about compression waves that behave just like sound does in the air. So seismic waves, they behave very much or almost identically to acoustic waves, and they have some of the same characteristics. Again, compression waves, we get lower frequency with distance, and most important, those waves can be influenced by other waves. So we can look at a very simple sine wave here to see how that works. Andrew? Good, Andrew. There we go. So here, we're just going to look at a single sound event, a very simple sine wave. Next slide. If we introduce another sound, and those sounds as they meet, they're very close to each other as far as being in phase meaning the peaks match and the troughs or the valleys match. Those waves get summed up and they actually get added and they influence each other. So the result is going to be, on the next slide, an amplification of that. So we will have a higher resultant wave based on those two input waves. The same thing happens if we adjust and we get those waves out of phase. So here you can see when we look at the red versus the blue, a peak is matching a trough, and the result can literally be a summation that comes out to zero or near zero. And it's a simple concept, but it's effective. It works in nature, and we have started using that in industry in the last probably 20 years, especially. Next slide, Andy. And just as an example here, hopefully you guys can see this, but we're all familiar, I think, with the noise canceling headphones that are advertised on TV, or if you go through an airport or anywhere, it records the sound and then plays it back out of phase and cancels the background noise out. On the bottom right is an advertisement for Porsche that are from an automotive magazine talking about how some car companies have employed noise canceling technology into cars where they have microphones in the engine compartment that play that noise out of phase through the speaker system and makes the cars quieter. It's interesting that some car companies like BMW and Porsche actually use this in the opposite direction, that where we saw in our example there where the waves were in phase and they created a larger wave, that they actually want to increase the sound of the engine in the cab, I guess, so the driver thinks he's got a hot car that he's driving around. So they actually enhance the sound of the engine in the cab. Again, doing this all with acoustics, with recording waves and how they're played back. Moving beyond that now is doing that mechanically. On the bottom left is an example of a table that is used for scanning electron microscopes. If you see on the bottom, there is two, those black boxes are actuators. And what happens here is there are vibration sensors that are built into the floor that this table sits on, and it records vibration, and those actuators move that floor exactly out of phase to the vibration, and it keeps that floor perfectly still to 6 decimal places, I think, in millimeters. literally perfect balance, and they're able to accomplish that using this concept of superpositioning of waves and canceling wave energy out. Next, Andrew. So again, in manufacturing, we use mechanical apparatus actuators to provide our out-of-phase motion to cancel that out. On the next slide there, so what do we do in blasting? A little bit different. Here, we're going to use the energy as our holes detonate to cancel out the vibration that's created from previous hole detonations. So we're going to go through the same process. And yeah, as Roberto said, these slides are in a PDF that everybody will have access to. So if I go a little bit fast, I'm sorry, but you will have access to all of these guys. So this is where the idea of vibration control came from. Came from looking at what we could do with acoustic waves and translating that into using that same application in seismic waves. Next. So I want to look at some waves again, but look at it more from a blasting standpoint. So we're going to look at 4 different blasts here, and I'm going to have represent a 5-hole blast. So each hole going off is going to create the wave you see at the top there, the individual wave. And then how those waves interact with each other and would leave the blast site will be represented on the combined wave at the bottom. So here's shooting 1 hole. So if we shoot 1 hole, our result is going to be the same type of wave. So what happens next, Andrew, if we go to shooting all 5 of those holes at the exact same time? So it's hard to see because those waves are stacked right on top of each other, but imagine there's 5 waves there. Well, when we sum them up, again, the peaks and the troughs match up, our combined wave is going to be much, much higher. And when those waves match up like that, and it gives us higher amplitude in our resultant wave, that's called constructive interference. Okay, next. So let's look at 8 milliseconds. And again, when you look at a seismogram and you look at those waves, remember that the x-axis, you're looking at motion versus time. And the x-axis is the way that we look at motion over time. So based on whatever the scale is there, if you see on the top there, our 5 holes have fired, and you see they've been staggered a little bit. And that stagger is the equivalent of 8 milliseconds based on the scale on the x-axis for this example. So we've put 8 milliseconds between them. But you notice it really doesn't help us because they're still in phase. They're still matching peaks and valleys. So we still get a much higher amplitude. We're still getting that constructive interference as a result of it. Andrew? So let's look at a different delay. We still have our 5 holes at the top, if you look up there, but now that we've spread them out to represent, for this example, the equivalent of about 42 milliseconds. And you can see what happens here. Now the peaks and the troughs match up, and where we have a peak and a trough and we sum them up, we get a result that's closer to 0. So the result of this is we can actually have lower vibration from our 5-hole shot than we did even from any of the individual holes and from firing a single hole. When we can use the energy in our shot to come up with cancellation like this, we call that destructive interference. And that is the basis of vibration control software, is to try to determine sequences of holes firing that will cancel out energy from adjacent holes or previous holes. Andrew? Now, what happens if we go even farther? If 42 is good, maybe a longer delay is even better. Well, again, we're talking about, sinusoidal waves here. So if you spread them out too far, you see what happens is we get back in phase again, and now our vibration goes back up. So there is no simple rule for a blaster, or no way for him to know intuitively or on his own whether shooting fast time between holes or between rows or slow times is going to give him that destructive interference he wants. It all depends on having to know what the shape of the seismic wave is that's going to be created by every hole when it shoots, and using that information to determine what delays are necessary in order to cancel vibration out rather than enhance it. Andrew? So I want to give you an example here, and what we're going to do And we want to make sure we leave time for questions here. But we're going to walk you through some software that does this. But again, a couple things I hope everybody keeps in mind is when we talk vibration control, we're talking blast design, fundamentals in powder factors, energy distribution, where your holes are distributed, accurate drilling, confinement, proper burden on the face holes. All that is going to play into not only a good shot from the results that you or your customer is looking for in fragmentation or muck pile development or whatever, but you find that when you have shots that behave the way you want and give you good results from a production standpoint, they're going to give you the best vibration results. And the shots that are poorly designed, that there's problems, or maybe you lose holes from drilling and the shots come out very, very chunky, you have oversized, the rock doesn't move, your vibration's usually really, really high. So we don't have to make a sacrifice between productivity and vibration control, whether that's to control vibration, whether it's a high wall or structures in the mine, the crusher, whatever, or buildings offsite. We don't have to sacrifice one thing for the other. Good blasts mean good vibration control, and they work hand in hand. And this is an example from a coal mine in the eastern United States. And this was the production shot that they had done the day before we came on site. And you can see the distances. Again, I'm sorry, everything's in imperial, but it's the numbers that are important more than anything. But at 1,200 feet or about 300 meters, we were at 1.28 inches per second in vibration. Right next to this shot, we went ahead and did a signature hole. Thank you, Andrew. That signature hole was identical to a production hole, the same diameter, same depth, same burden off of the free face. Just, it's as if you're drilling a production shot and you just stop after the first hole. Okay, loaded with the same product and shot, and you can see the distance is identical or almost identical, and the particle velocity from that single hole is a 0.51. That data was then run through a vibration control program that took that waveform. Go back one, Andrew. Thank you. So that wave that you see there, those three waves for our three components, transverse, vertical, and longitudinal, that becomes our building block. And I believe the shot size for this mine was about 150 holes. Wasn't really big, but in essence, in the model, we used that wave that you see there 150 times to represent 150 holes firing. And the software ran algorithms to determine what delay between holes firing by moving them on that time axis, the x-axis, back and forth, doing it systematically, and then summing those waves up would give us the best vibration results. And then that's all it does, is it gives us timing recommendations then that we can pick. So go ahead, Andrew. The next shot, which was I did right next to it, you can see the distances. Actually, I was a little bit closer, but same pattern, same number of holes, same pounds per delay, same pounds per hole, and we cut vibration by 36%. That's not making any other change, doesn't cost the mine any more money. They're not paying for more labor, for more drilling, for more products. It's a simple change in the timing that is used in order to facilitate this. And with electronic detonators, with most of the systems, you have 20,000 delays, 0 through 20 seconds in 1 millisecond increments. So this gives us an amazing tool in order to come up with and find precise timing using software based on that signature hole that's recorded in the field. So it's responding to site-specific geology. The shape of that wave is determined by putting that pulse in the ground by that signature hole, that test hole, letting it rattle through the ground and recording it at our critical structures. So the shape of that wave is basically a geologic signature of seismic transmission through it, hence the name signature waveform. We use that over and over again to simulate a large shot, sum up the waves, and here's what our result is. And here we're showing a reduction of 36%. So real simple, that's the way basic vibration control software works. It has gotten much can be as simple as that, and there are programs on the market that you can run in. Once you have that signature hole data, you can literally run in 10 minutes to come up with predictions for simple shots. Maybe takes a little bit longer if it's a complicated pattern, or there is much more complex software that does a lot more for you. I'm going to have my cohort here, and Andrew Johnson. Andrew's again a graduate from Missouri from the Rolla Mining School. Some of you might have heard of, and he's going to walk through one of the software platforms that's available. This is the Paradigm software that was developed by Dr. Cameron McKenzie out of Australia. Bill mentioned him too. Super good guy, super smart guy, and this is the basis of one of the vibration tool that we use in our blast designing tool here at Austin. And Andrew, I'm going to turn it over to you and go ahead and walk us through how we go about collecting, recording, and using this data to come up with timing in the field.
All right. Thank you, Stuart. Good to be here with everyone. As Stuart's mentioned a couple times already, one of the big things is you've got to have proper blast design in order to get vibration results that benefit you, your company, whoever it may be. But what we do with the Paradigm software, as Stuart mentioned, is one of the big things is we have to identify the critical locations for each blast. So that can be internal locations such as primary crushers, storage silos, mine site buildings, any regulated structures that cross the property, and even extending into external critical locations such as residential buildings that may be getting close to the mining property, commercial buildings, any public roads, bridges, power lines, any number of things. So, and a big part of vibration analysis and making sure your vibrations are what you want and good is you've got to be able to determine where your future mine plans are. You know, this goes into setting up the locations for where you want to get signature hole data from, and being able to drill those in areas that you are going to in the future, even if they may be 6, 12, 18, 24 months into the future before you start mining in those areas. It's the seismic data will never go bad. It can be used 2, 3, 4 years down the road. So if you've got the capabilities and are able to, it's always good to get the data early and be able to sit on it and have it ready to use, then try and scramble to collect the data as once problems present themselves. And this all goes into, you know, with the signature holes, we want to make sure that they are loaded the same way, they have the same burden and relief that a normal production hole would have. And when collecting the signature hole data, you want to make sure that your seismographs are set up correctly. There's no room for movement in the seismograph, because if you're getting bad data from your signature holes, you're going to have bad data to try and make any predictions with or analyze your vibrations. So, and as we've mentioned already several times, that vibration analysis, it begins with your shot design. We've done this on manually laid out shots by the blaster. The day of a shot, he'll lay off another shot in the pit in a different location, or using a UAV drone and doing 3D models, and being able to use this and use smart drills. It definitely helps in being able to control vibrations more. And once we've done this, and we have the design set as what it's going to be drilled like, then we can start diving into more of the vibration analysis and creating the best blast plan, going forward. As Stuart mentioned, we use Paradigm software as a big part of our vibration analysis, and In the software, we are able to produce any timing combination that you could want to use possibly. Anything from a fixed per distance scenario, which is going to be you will assign a certain delay in terms of milliseconds per foot, and tie the holes together in your shot, and it will measure and look at the distances between those holes and assign the delay period as needed. We can do a fixed per hole scenario, echelon scenarios, really anything that works, any timing scenario, we can use that and come up with a version that will work. These are some just very basic tools that we look at when we are doing our timing vibration analysis. We can see how the shot is going to progress in terms of which hole is going to fire when. Useful to see, making sure that you don't have holes in front of something that shouldn't be going off yet, or holes behind something that shouldn't be going off yet, as well as timing contours. So if you have in your operation, if you have certain benches that tend to shoot better a certain direction, you can make sure the timing plan you came up with is getting that rock moving the right way to give you the best muck pile and vibration results. Same with the burden relief and interval graph. Here's the initiation animation that I was talking about. So as you can see, we can follow and we can see as how the shot is going to progress as the holes are detonating. It's a good double check, make sure the timing's correct, make sure nothing's funky is going on. These are the timing contours, so we can see the direction, general direction that the shot is going to move based on the timing. This could also be affected by geology that we don't see, so it's definitely something that helps with the consideration when coming into timing. Burden relief. So this is showing from the row to row how much time and movement the rock in front of each hole is going to have before the hole detonates itself. So it's a good tool to use to make sure that you've built enough time to allow for rock movement and get the correct burden that you're looking for on your design. And here, looking at the interval graph, we were able to see if we have more than one hole that is designed in the timing scenario to shoot at the same or within a certain delay period. This is beneficial when it comes to limitations of weights, charge weights, or holes firing in a given interval, such as what Stuart was mentioning with the 8 millisecond rule. This is where we really get into being able to optimize our vibrations, and everything else is using these tools here. But first, we have to optimize our basic design, and then we're able to analyze the vibration and fine tune the results to what we're looking for. And using these tools, we are also able to get a rough vibration prediction for the shot. If that is something that is needed, or if it's a more critical area, we know beforehand going into shot day, what is going to be the rough vibrations. Continuing, here we can see data from the signature hole testing can be accessed. It allows us to determine critical structures and what data to use. So don't know how well you guys will be able to see it, but the blue dots are seismograph locations, and the black lines are fault going towards signature holes. So the signature hole data, you can trace back from the points to the seismographs, and those seismographs are using the data that was collected by shooting those signature holes for future consideration when determining vibration predictions. You can also see the shot pattern. including the nominal timing created to allow for its accurate determination of data. The location of the pattern, signature test holes, and critical structures is all used by the software. We'll see in more detail what that kind of looks like here over the next couple of slides. In many cases, our signature holes are recorded with reduction blast, and we're able to, using the software, we're able to clip the waveform of the signature hole itself. So as you can see here, on the longitudinal, transverse, and vertical waveforms, we're able to see where the signature hole was fired, and we're able to use that and clip that data to use for future models, future considerations. This is one of the tools that we can use to find and dial in our timing design to create an optimized timing plan. So if we know the propagation velocity, it can be entered. We can also weight the different structures in different seismograph locations. If one is closer and it's of more importance, we can weight that one heavier in the model, and in the simulations, it will adjust accordingly. Or if everything's all the same importance, we can leave the weighting the same and it will determine the best from there. Looking at the delay periods, this is going to run in simulations and look at the different timing schemes that could possibly be created from a plus or minus 5 milliseconds of the delay. So if one delay that in the generic timing scheme that you create is 21 milliseconds, it will look at a range of 16 to 26 milliseconds to analyze and look at and try and optimize the vibration results. Additional analysis is based on the Monte Carlo technique. This allows us to introduce randomness to the timing variables and to come up with the best delay sequence. The Foresight tool, which we'll get into more here in the next couple of slides, allows us to simulate the blast any number of given times to get a prediction of the resultant vibration using whatever timing sequence. So here's the results of the Foresight tool. As we can see, the results, you can sort them by your peak particle velocity, your PVS, your frequency, and your perception index. And your perception is going to be a result of your PPV and frequency. So the lower your perception, the idea is the less impact it's going to have on your seismograph location. So, and this is another tool to where you can select to choose either certain seismograph locations to look at to optimize your timing for, or in this case, you can look at 3, 4, 5, even different seismograph locations. And you can weigh the results based on your PPV, frequency, perception index, any number of factors to be able to select the best timing solution for that specific shot. Moving ahead, you're able to select, optimize electronic timing to ensure compliance at all nearby sensitive receivers. We get those results through using the Sweet Spot tool and the Foresight tool. And we're able to apply weighting to see which seismograph location is a more sensitive location, or if they're all just as sensitive, we're able to leave the weighting the same. And this is another tool we are able to use in the Paradigm software. It will allow us to identify directions of vibration enhancement due to the timing sequence, timing plan, and allows us to see the impacts of what the vibrations will be 360 degrees around the shot area. So just to kind of tie everything all back together, when using the Foresight tool, we're able to see a rough approximation of what the waveforms will look like, along with predicted PPV average, amplitude, and general frequency. So if the selected timing that we either use or come up with does not meet our expectations, we're able to go through these tools multiple times, make adjustments in order to find the best sequence and timing plan for us. We're able to see what the predicted vibrations are when compared to compliance criteria such as the Z curve shown here. It's a really useful tool, especially operations that are little more sensitive to vibrations, either because of close neighbors, important structures that are nearby. Being able to see this and know confidently going forward with this shot that the timing sequence is correct and should have no issues as far as regulatory compliance is good to know. Now, and at the end of the day, it all comes down to it all starts with a good blast design and making sure that's correct and not just throwing a design on the ground and painting some rocks and going, we'll figure it out. Because these tools, while they are good to use, they still are only as good as the design they are working with. So like I said, these tools, they give us the lowest rough prediction of PPV. This is not something that you can follow by the book and follow this prediction. It's very rough, but it's a great starting spot. And overpressure, as we all know, is another major issue when it comes to blasting. Overpressure is a major cause of complaints regarding blasting, accounting for as much as 75% of any blast-related complaints. The software that we use, it can provide us an approximation of expected overpressure that can make perception of the blast even more noticeable. As you guys can see here, this is showing the wave fronts from the individual holes detonating. So we're able to see how, as the shot progresses and gets farther away from the location of it, how the air overpressure is being dissipated as it goes out over time. The software also allows us to take a look at fly rock predictions. So as you can see here, the yellow is a safety factor of 2 that was decided upon with the customer. The red circle around the shot is the maximum potential fly rock range based on the shot design, load plans, timing. And if you see the light green circle, that is the max potential fly rock for a specific selected hole. And on here, you can also see how close the shot was to any potential neighbors, any potential structures. And this is the same thing, but in a 3D view. So the yellow is, once again, it's a safety factor of 2. And the red is, once again, the maximum potential fly rock range for the whole design. And as you guys can see in kind of the top left corner, that is how close this design was to neighbors. So, once again, it comes back to blast design. So While the use of vibration control software can be a useful tool towards minimizing impact in both near and far field, it cannot overcome the laws of physics. Vibration control will always be based on a sound blast design, as we've mentioned multiple times this afternoon, and an accurate application in the field. So this is making sure that your drilling is done correctly, you're selecting the right products to use for your blast, any special geological considerations that must be taken into account, and any regulatory limitations that you will face regarding your specific operation. So. I think that's it.
Thank you very much for your presentation, sir.
Okay. Thanks for the great presentation, Mr. Johnson and Sir Stuart. Now we're going to enter the question and answer section, and I will proceed to mention the questions asked in order to clarify the topic. Okay. The first question is from Luis Marino. What type of site-specific geology data must be considered in a well-done vibration prediction model? Simplistic divide model doesn't consider macrostructures, faults, discontinuous, but should we consider information such these ones in a vibration prediction model?
Yes.
John Watson here. Are you there?
Yes, I'm here. In response to the question of what site-specific geological data must be considered, it really depends on your site. If you have a lot of neighbors that are close, as in like the picture that Stuart we had in the beginning for the quarry, the mining operation on the West Coast, if you have non-mine owned structures that close, having site-specific a geological profile of that data, that's going to be really beneficial to being able to look at your vibration control and being able to optimize everything. But if you're not in a situation like that, a lot of the work I do, we don't necessarily consider a lot of the geological data because it's consistently the same rock type, and what faults, voids, caves, anything like that, determine more overall shot performance in terms of fragmentation and loading plan, and have a smaller effect on the vibrations. So.
Okay, thank you. The following question is, how can we measure the effect that increased delays between blast holes produced to the granulometry? 7 milliseconds is optimal when we want to have a good fragmentation. 42 milliseconds between blast holes is the best when we want to minimize the vibration result. But how we can predict and have an idea of how much this change from 7 to 42 is going to affect the final fragmentation and the P80 value?
I was talking to myself. I'm sorry. That's a good question. We really didn't get into vibration or excuse me, fragmentation analysis here as part of it. There is a connection between vibration, I think, between fragmentation and vibration, that when you model for low vibration, you optimize your blast from a standpoint of fragmentation. But putting that as far as in a model to predict fragmentation, there's software out there. I know what we use has a fragmentation prediction algorithm in it. So does a lot of stuff on the market, but I'm not really sure how you would get ahead of that from the standpoint of trying to dial in just based off of timing. I'm not sure that's something that you can do just with timing.
Thank you. The following question is from Luis Marino. He mentioned, I work in a mine site where nowadays we blast more or less 500 meters away from closest houses on the neighborhood community. In few months, we will be blasting only 300 meters from closest houses. We have nailed PPV control, so we have gotten good results on this variable. However, our greatest challenge today is vibration frequency control. Part of our blast deliver low frequency waves, 10 to 15 hertz. Those human perception and masonry structures response are more clear. Question, can we shift this frequency up? And if so, what type of effort should be done to achieve this goal?
Okay, that's a good question, and it brings up a very good point. We often talk about shifting frequencies when we talk about vibration control. You can't shift frequencies. There's just no way to do that. What you try to do is use that destructive interference that we've talked about today to minimize the low frequency end of the spectra. For structures, anything under 20 hertz, usually you have an amplification of the structure, and you can't push your frequencies of your vibration higher than that. But what you can do through using linear superpositioning and modeling is try to cancel the low frequency that's in those waveforms, so all that's left is higher frequency waves. Now, that also has a lot to do with the geology. In some geologies, there's just really no way to do that. The characteristics of the wave going through the geology, it's transmitting all low frequency. So while you can reduce the amplitude by reducing that, you can't really end up with higher frequency data because there's just none in there to begin with. But that's the whole purpose in using this kind of technology of recording signature holes, running analysis. Most of the programs have the ability to analyze for amplitude, for the lowest particle velocity, or analyze for frequency, with the idea of canceling out as much low frequency energy as possible, just leaving the high frequency. Unless you have a regulatory problem, you're much better off with a higher amplitude and higher frequency seismic energy leaving your property than you are with low amplitude and low frequency. So unless you run into a problem that you're up against a regulatory limit as far as amplitude, any of this software, vibration control software, you should be able to use to come up with, to have it give you suggested timing that'll give you the best frequency spectrum that geology will give. And again, it's all dependent on the geology. If it does not transmit high frequency energy, there's not a whole lot you can do with it. But at least you know that, and knowing that is important. If you know the limitations of what you can do with technology for a given geology, then at least it gives you a better idea of what you can and can't do.
Thank you. And the following question is from Amak Hassan. He mentioned, how about spacing to border radius, subdrilling factor like subdrilling, impedance mismatching, and other factors.
I'm not sure I understand the question there. I apologize. Let me see if I can look at it. Is it on one of the chat messages?
Yeah, really, when you're looking at what pattern you're using, there's really no answer of saying and I'm sorry guys, this will be in imperial units, but a 12 by 12 foot by 14 foot pattern compared to a 11 foot by 14 foot pattern, that the vibrations are going to be different. There's too many other considerations, even when looking at how much subdrill to have on your design. That all more or less goes into making sure that your fragmentation is what's being desired for either your operation or your customer, and maintaining floor level and things like that. Hole size will have an effect on your vibration, just because the bigger hole means more pounds. But in the grand scheme of things, the pattern has, at least from what I've seen, very little impact, if any at all, on the vibrations.
Thank you. We have other questions. Is the Clearance Zone 3D software available for purchase?
I'm not familiar with that software. For vibration control, there are some programs out on the market. Weight Seismology has an Alpha Blast program that I highly recommend. It does very nice work. iBlast from Blast Dynamics out of France, Thierry Bernard, has a good vibration control. It's very, very complex. It requires a lot of information on rock properties, but does a very good job of predictions. So, and OPIT Blast, I think, is coming out with a vibration sequencing. So there's things available out there that you can look at. You can also contact consultants that might have software programs that they are using internally, and but that are willing to apply on a case-by-case basis.
Okay. The following question is, what is the small separation of char timing have you been able to model and still maintain desired vibration levels or frequencies?
John, it depends on geology, but we have shot, and it depends on what you mean by separation of charges. I mean, we've been able to do significant reduction in vibration where we've had up to 6 charges firing within an 8 millisecond window within a shot. So, I mean, as far as separation, sometimes they're only a millisecond apart, because again, it's all depends on where they are in the shot and the wave shape that is being transmitted by the geology. So I don't really think there's a minimum separation. I mean, you can get down to shots that on paper their holes firing within a millisecond of each other, but still are affecting significant vibration reduction and vibration control, or again, enhancing the frequency spectra by canceling the low frequency out. It's why electronic detonators are so important now, to have that millisecond accuracy, because sometimes we need to have that. And there are some techniques that consultants are looking at that are talking about needing 1/10 of a millisecond detonators and accuracy in order to achieve some of the things that are being suggested. So we're not at the end of this by any stretch of the imagination.
And to add on to that, kind of the most consistent separation that I've seen used is about 4 milliseconds. That seems to be kind of our go-to. But as Stuart mentioned, you know, there's a lot of other variables that play into that. So
You know, the thing that you really have to remember is you have to, as we say, drink the Kool-Aid, or you have to buy into that the software works. And when you do a good job and collect the data correctly and apply the vibration control software, and it delivers a timing sequence to optimize to, you really have to believe in the theory behind it, and that it's going to work. So when you time out a shot and you see you have 5 holes per delay and holes shooting a 1 millisecond apart, you have to remember that it doesn't matter what it looks like on paper. What matters is what that seismograph picks up, or what that structure you're concerned with, what it's actually impacted by. It's the results that's all that matters. And in some cases, especially when you start, it takes a little bit of a leap of faith, or a lot of faith that the technology we're talking about here works. This was developed back in the early 1980s. So this is not new technology. Some of the applications, of course, are that we've made, you know, significant changes. It used to take all night to run a shot design on a mainframe computer that a laptop will do in 20 seconds now. But the concept and the theory behind it is still the same. We just have better tools, better predictive tools, better tools to use in the field with electronic detonators to achieve better results. But you have to trust that the system works, or it gets problematic if what you see on paper is not what you're used to, and you get uncomfortable with it. Been there, understand it, dealt with a lot of people that way, but it works. The proof is in the results of it, and it's great technology.
Thank you. The following question is, which drilling pattern is required to control vibration?
A good drilling pattern. Again, it goes back to a sound blast design. So there's nothing special about one design over another, but your drilling pattern has to be consistent with proper energy distribution throughout the shot, and being able to break rock efficiently. And there's not one pattern. Andrew, I'll be interested if you have seen something different, but a staggered pattern, a rectangular pattern, a square pattern, they all have the same ability for vibration control. Again, it's just sound blasting practices that we certainly have not had the time to get into in the last 2 weeks. But in doing that, you've gone a long way.
Yeah, I mean, when looking at your pattern, square, offset, rectangle, trapezoid, triangle, whatever it may be, there's really too many variables that are unaccounted for when just trying to look at that one thing to control your vibration. Your geology is going to play a big part. Hole size, product selection. I mean, I haven't seen certain patterns perform better. So it really too many variables to just be able to focus on one to control.
Thank you. What is the biggest mistake you see people make when collecting signature waveform data in the field?
Probably the biggest mistake I've seen is the signature not being able to be treated like a true production hole. You know, whether it's on the face or back away from the face and confined, it's, you know, not able to load that hole and shoot it like you would a, say, a production hole in the middle of your next production shot. That's the biggest mistake I've heard of. It's the biggest mistake I've seen. I don't know, Stuart, there may be other factors that go into it, but
Thank you. The last question is, when you guys speak about ways superpositioning, can we do that only at just in times, or should we blast two simultaneous holes in opposite ways to one cancel the other?
really with the technology we have now, like Stuart's mentioned with the electronic caps and detonators, if you're able to come up with an optimized design to cancel the waveforms out, that's that should be a goal. It's not something that's necessarily going to happen every time, but as Stuart, as we showed with, if you're able to match your peaks with your troughs, even just closely, you're able to make the resultant sum of all wave be a lot smaller than it would be if each hole was set off either instantaneously or with a different delay. So that's one of the benefits of these, of the electronic detonators. So
So now we are going to end with Noé. Thank you, sir. Noé.
Yeah, please. Roberto, could you share your screen, please?
Yeah.
Thank you. Okay, good evening to you all. My name is Noé. Sorry, I will turn on my camera. I thank you all for having joined us today. Hope you're having a great week. This was the blast design and pattern for vibration control part 2. We want to give special thanks to Mr. Brashear and Mr. Johnson for such an amazing webinar. Thank you so much for your willingness or sharing some of your knowledge with us. Also, we want to thank Mr. Watson for supporting us during these 2 webinars. Without him, any of this would have been possible. Okay, before ending this webinar, we want to invite you guys to the IC Peru webinar, which is today too. It's going to start in 1 hour approximately, and it will be held by Mr. Chung Kim. He's going to talk about bulk products. So if you're interested, you can find this webinar on their Facebook page. Roberto, could you pass to the next slide, please? Okay, our next webinar will be on May 6th, and it will be in charge of Mr. McClure. He's going to tell us about drone technology at mining, and we will be sending the invitation to your emails, and we'll be posting the flyer and link description on our Facebook and LinkedIn in the next days. So finally, here in the ICPUG student chapter, we have this tradition to shout out fire in the hole at the end of this webinar. So please turn on your mix, and on the count of 3, everyone shout fire in the hole, please. So, okay, would like to unmute themselves. Please turn on your cameras to end this webinar. Hi, everyone. Please turn on your cameras. Just to finish, just 5 seconds. It will not take more time.
We would like to know from which country do you come from. Queremos saber de qué país nos saludan.
Yeah, please. 1 second, please. Let's wait just once.
From Spain.
Greetings. Salute. Okay. So I guess we're okay now. I will count down. Try to turn on your mic on at least, please.
Turn on your
Okay.
Please.
So
Everyone, your micros on, please.
Hear me?
okay.
Yeah.
So 3, 2, 1. Fire in the hole.
In the hole.
In the hall.
Fire in the hole. Fire in the hole.
Thank you all. Hope to see you in the next webinar.
Thank you
Take
very
care.
much.
Thank you all. Thank you, Stuart. Thank you, Andrew.
Thank you.
Thank you.
Thank you.
so
Thank
much.
you, team. Peru.
Thank you. See you in the next webinar.
Hello.
Yeah, thank
you.
you, John. Thank you, Roberto.
Yes, Stuart.
Thank you, team.
Thank you, sir. Thank you very much, sir. Thank you, sir. Thank you, sir.
Thank you, John.
Thank you.